So my talk for today is entitled Microwave Carbon Synergy for Biomass Valorization. And as written in executive summary in the promotional flyer, this will be the contents of my talk. So I will start with the introduction of microwaves. What is it all about and how microwave can accelerate reactions, followed by carbon. And after introducing those carbon materials, I will also talk about the synergy of microwave and carbon, especially its application to conversion of biomass into useful chemicals and fuels. At first, let me introduce to you some of the carbon materials which I believe you are very much familiar with. We have the carbon chains, of course, polycyclic aromatic hydrocarbons. We have amorphous carbon. We have C6T, or the fullerenes, C7T, carbon nanotubes. Sometimes we call this one-dimensional carbon material, and nanodiamonds. And of course, we should not forget graphite. Now, talking about graphite, we can actually separate those two-dimensional layers from graphite by exfoliation. And these two-dimensional sheet that we can obtain from graphite, we call it graphene, which is, I could say, a very versatile material. And these can also be the carbon material of the future. This is graphene. And as I have mentioned, this is a carbon material of the future. Why? Because this is the world's thinnest material. When we say thinnest material, it is only one carbon atom thick. One carbon atom thick. That's around 0.34 nanometer. And other than that, this is also recognized as the toughest two-dimensional material. This is even harder or tougher than steel or diamond of the same dimensions. This graphene is also light. It weighs just 0.77 milligrams per square meter. That's how light graphene material is. And this is also flexible. It can be stretched up to about 20% of its size. Other things about graphene, it has many amazing electronic properties, like, for example, extremely high electric current density. So it can be turned into a superconductor. That's why the use of this graphene material is promising, especially for the development of semiconductor materials. All right. The problem with graphene being isolated from graphite, that's not a very economically feasible method, or I should say not a cost-effective method. As an alternative, we can also apply the chemical route. And one of the chemical routes that we can think of for production of graphene is by Hammer's method. But this involves oxidation of graphite. When you oxidize graphite, it will form graphite oxide. This is graphite oxide in its form. It has those layers of graphene oxide. You exfoliate those layers of graphene oxide, you get graphene oxide. And this is the structure, all right, of graphene oxide. You have those oxygen functionalities on the surface of graphene oxide. This is not graphene. This is graphene oxide with those oxygen functionalities. If you would like to get or obtain graphene, you need to remove those oxygen functionalities. All right. So these are some of the possible active sites in graphene oxide, which you can use as catalyst. Like, for example, acidic or basic groups. It also has carboxylic groups, the COOH, and a very unstable epoxide, right? So epoxide, you form OH groups and H plus instantly in the press in water when you dissolve this in water. So the presence of these active sites make graphene oxide surface highly acidic, as I have mentioned. Now, these active sites or functionalities on graphene oxide surfaces can also be found in hydrochar. We did experiments or we did research on the conversion of these biomass into biochar under hydrothermal conditions. And we also found the presence of those functional groups on the surface of hydrochar obtained at around 200 degrees centigrade in 1 hour using microwave assisted hydrothermal carbonization, like this one. Uh, these are some of the FTIR spectrum that we can get or we can get from analyzing the surface of sago biomass hydrochars obtained using our approach, the microwave hydrothermal carbonization. And using SEM analysis, in TEM analysis, we also found some amazing structures like the presence of carbon nanotubes and some spherical shapes carbons present on the surface of the hydrochar we got from sago. Now, the presence of these functional groups on the surface of graphene oxide or even sago hydrochars make these carbon materials having great affinity with microwave. So it has a strong microwave absorptivity, and as evident from the values of the loss tangent. As you can see from this slide, the loss tangent for graphene oxide, because of the presence of those functionalities, is far much greater than water. We know that the water has a very high microwave absorptivity, but as compared to water, it's even 5 times higher than that of water. And because of this higher affinity with microwave, we can say that the synergy of microwave and surface functionalized carbon-based catalysts can significantly accelerate the reaction. Allow me to share this video in order to further explain the microwave and carbon synergy. So here in this video, microwave is applied in pulse mode. When we say pulse mode, the microwave is on for only about 0.5 seconds, and it's off for 4.5 seconds. The solvent is decane, which is relatively microwave transparent. It doesn't absorb microwave. And the thermocouple monitors the bulk temperature. That's actually the temperature of decane. The boiling point is 174 degrees centigrade. The carbon material is in decane as well. And The moment you apply microwave, instantaneously you get those bubbles forming. And these bubble formation, we can actually interpret this as that the surface of the carbon reach the boiling point of decane, which is 174 degrees centigrade, the moment you applied microwave on it. If you look at the bulk temperature, which is the temperature of decane, it only reaches about 70 degrees centigrade after 2 minutes. So we can say that microwave is selective to heating of carbon. It, it doesn't heat the decane, which is the solvent. It's internal, right? And it's very rapid. Rapid, I will repeat, uh, it reaches the boiling point. The surface of carbon reaches the boiling point of decane at the instant you apply microwave. Okay, so here in Kumamoto University, we apply this synergy of carbon catalysts because this can be a source of Lewis and Bronsted acids. And microwave, which is selective, internal, and also has rapid heating to intensify reactions. We call this our green approach for process intensification. Green, this is sustainable. It utilizes, of course, clean microwave energy. And it's green, all right? Environmentally friendly. And separation of the materials from the products is easy because, as you know, carbon is a solid material. So we apply this to conversion of biomass into useful chemicals and fuels. And talking about biomass, the most abundant material in biomass is cellulose, right? So we first apply our method, the microwave carbon synergy, to conversion of cellulose into more digestible sugar like glucose by hydrolysis. After getting glucose, we can further convert this into even more useful chemicals. One of this is 5-hydroxymethyl furfural. This 5-HMF can be a raw material for production of even useful chemicals, resin materials, plastics, biodegradable plastics, biofuels. This can also be used for production of pharmaceuticals. Okay, so let me talk about the details on how we can convert cellulose into glucose first using this microwave carbon synergy. We use this experimental apparatus. It's Mars 6, and we put the sample inside the reactor. The reactor is about 100 ml. This is microwave transparent reactor, Teflon, which can be used up to a pressure of 3 megapascal. That's 30 bars or 30 atmosphere, and temperature up to about 250 degrees centigrade. And this is an example on how we can achieve the reaction temperature by ramping it up at first, normally about 15 minutes, followed by holding time for the reaction to occur. We normally apply a microwave power of about 400 watts, but this can be higher depending on the materials or even lower than 400 watts. Okay, so now for cellulose to glucose conversion, as I've mentioned, we can achieve this by hydrolysis. And normally this will require a very high temperature of 400 degrees centigrade using only water. But that will require very high pressure as well, other than high temperature. So as much as possible, we would like to lower the operating conditions. In our case, using microwave and carbon synergy, we were able to lower the temperature to about 200 degrees centigrade and getting glucose yield of 61% in the first cycle. And this is due to a very high affinity of graphene oxide with cellulose. So the process undergoes surface attrition first, followed by protonation that will aid hydrolysis of cellulose in order to get glucose. The results actually are published in Green Chemistry. And well, we can also use, instead of graphene oxide, a more stable reduced graphene oxide. But this will require a relatively higher temperature of 220 degrees centigrade. So reduced graphene oxide performs similar to that of fresh graphene oxide in order to get glucose, but as I have mentioned, at a relatively higher temperature. The good thing is reduced graphene oxide is more stable than that of graphene oxide. Now, after getting glucose, we can convert this into more useful chemicals. And that is by isomerization process. Here, we need Lewis acid in order to get fructose and Bronson acid for dehydration to form 5-HMF. And we were also successful in getting glucose conversion of 85%, but the yield is relatively low at about 25% at the moment for 5-HMF. We tried various carbocatalysis other than graphene oxide. We also use reduced graphene oxide. We even compare it with nanodiamond and graphite. We even dope reduced graphene oxide with metals such as copper and tungsten in combination with the reduced graphene oxide. And we check the ability of these various type of catalysts on the production of 5-HMF from glucose. And we found out that among these catalysts, still reduced graphene oxide perform the best. Now, how about conversion of this time the oil components of the biomass? So we were successful with the cellulosic components. Allow me to introduce this time the oil components of biomass. When we talk of oil components, we are referring to the triglycerides and the free fatty acids present in the biomass, especially the seed oil. Now, in this case, this is an example of the transesterification for biodiesel production. And here we applied in situ transesterification. When we say in situ transesterification, we did not extract the oil present in microalgae. We just added the solvent, which also serve as reactant for the transesterification methanol. Methanol is capable of extracting those oil present in microalgae. And here, we also apply microwave and graphene oxide as catalysts. And as a result, you are getting highest yield of biodiesel, which is the fatty acid metal ester of about 96%. So the results have been published. If you are interested, you may want to also browse the results in this journal. So this is promising because normally it undergoes, the drying. We can avoid the highly costly process of drying microalgae followed by extraction of the oil. But this is in situ. The methanol will react at the same time extract the oil present in microalgae using microwave. And the good thing is with microwave, we can also disrupt the cell wall for more efficient extraction of the oil present in microalgae. Now, we are also interested in the utilization of glycerol. This is actually the byproduct of biodiesel production. So for every, let's say, about 10 kilogram of biodiesel we produce, we also produce about 10 kilogram of glycerol. And we also need to think on how we can utilize glycerol in order to produce useful chemicals. And for example, here in Japan, the glycerol production reached 39,200 tons 3 years ago. And we expect this to increase in the future. So in our case, we convert this glycerol into what we call GTBE, glycerol third butyl ether, by reacting glycerol with alcohol, third butyl alcohol, in order to produce these GTBE molecular structures. Example of this is MTBG, monothird butyl glycerol. It has high solubility in BTF, the third butyl glycerol DTBG, and tri-third butyl glycerol TTBG. So we applied our method of microwave carbon synergy in order to convert these glycerol into these useful chemicals, MTBG. The purpose is after getting this GTB, glycerol third butyl, we can actually add this to biodiesel in order to get high quality BDF, because adding glycerol third butyl ether to biodiesel will increase its Quitain number. So this is actually the main reaction pathway for the esterification of glycerol to produce MTBG, DTBG, and TTBG. There is a side reaction, which is the disadvantage of using TBA. TBA can be dehydrated to produce isobutene as well. And isobutene has a very low boiling point of -6 degrees centigrade. So after forming isobutene, it will evaporate and escape from the reaction zone. That's the problem with the use of third butyl alcohol. Anyway, we were successful in converting this glycerol by reacting TBL in the presence of graphene oxide. And we compared the results with that of the commonly used amber list 15. And as a result, we found out that graphene oxide performs better than amber list 15. As I have said, graphene oxide is highly acidic because of the presence of the functional groups on the surface. And that could be the reason for these promising result with the use of graphene oxide as compared to that of Amberlist 15. So we even tried to explore other types of graphene oxide-based catalyst. Like for example, instead of using hammers, commonly used hammers method, we also tried using the Tours method. And we also tried to ozonate the graphene in order to get the ozonized graphene oxide. And we also compared it with reduced graphene oxide and so on and so forth. And as a result, we found out that among those graphene oxide-based catalysts, we got the best results still using the graphene oxide obtained by Hammer's method. And well, we tried to further analyze why we are getting this, the best result with Hammer's graphene oxide. We tried to analyze the surface acidity using ammonia TPD. We found out that the ozone-treated graphene oxide has the highest acid intensity peak, but talking about acidity, Tours graphene oxide has the highest acidity. But a balance of these acid intensity and acidity on the surface of that catalyst, among these catalysts, is still, we should say that graphene oxide obtained by Hammer's method perform the best among the catalysts. So, so still we are into using graphene oxide using Hammer's, obtained by using Hammer's method. As I've mentioned, there is a drawback on the use of tert-butyl alcohol because of its dehydration in order to form isobutane and water. So we also thought of pressurizing the system using carbon dioxide. Somehow, pressurizing the system using carbon dioxide will push isobutane back to the surface of carbon catalysts. And adding carbon dioxide, we know that carbon dioxide reacts with water to form carbonic acid. Somehow, the formation of carbonic acid will also add up to the acidity that is already present on the surface of graphene oxide. So we tried this one. And this is just a preliminary result. We are getting, well, I should say, positive result on pressurizing the system with carbon dioxide. Again, the addition of carbon dioxide will push isobutane to the surface of the catalyst for further reaction. And carbon dioxide will also react with water in order to produce carbonic acid, which will add up to the acidity on the surface of the catalyst. With regards to catalyst reusability, we can actually use the catalyst for 3 cycles. It's really stable. However, probably because of the loss of those functionalities on the surface of the catalyst, there is a disadvantages on the selectivity of the desired DTBG and TTBG in the products. So Well, we also examined the changes in acidity of the catalyst before and after the reaction. And we notice this is actually the reason probably why the selectivity to the target DTBG and TDBG decrease. So this is the summary on the use of graphene oxide or graphene-based, carbon-based catalysts on the production of glycerol tert butyl ether from glycerol obtained from biodiesel production. We also use sago-based hydrochar, biochar. As I have mentioned, we can utilize those functionalities present on the surface of biochar for um, some catalytic reactions. And we also use these biochar for production of GTBE. Although the total yield is lower than that of graphene oxide, this is still higher at about 55%. The functionalities on the surface of biochar may not, or I should say, not comparable with those acidic functionalities present in graphene oxide, but still we're getting yield above 50% using sago-based hydrochar. And we even tried pressurizing the system using carbon dioxide. And we also get promising result by pressurizing the system using carbon dioxide and using the biochar obtained from sago biomass. What will be next? In our next project, we will further explore this microwave carbon synergy. And this is for the valorization of blue carbons. A very good example of blue carbon is kelps, seaweeds. In order to convert these materials into useful chemicals, for example, bio oil for aviation fuels, production of aviation fuels, sustainable aviation fuels, I should say, and also biodiesel. For the HS phase, we can actually obtain some organic acids, proteins or peptides, and some sugars in the HS phase. The solid phase, or those hydrochar or biochar we can obtain from blue carbon materials, can also be used or utilized as acid in order to intensify the chemical reactions. So that will be next. And we got this project from the Japanese government in collaboration with the Thai team in order to valorize those marine seaweeds and also microalgae. So, well, allow me to again show the executive summary. I should say that microwave accelerate reactions by avoiding the preheating stage. That is a feature of the conventional method. And carbon, as you know, is a sustainable material. This can be easily separated from the products being a solid material. And utilizing these carbon materials having those oxygen functionalities as a catalyst can significantly reduce reaction time and energy usage. The synergy of microwave and carbon, I should say it's a very efficient, environmentally benign, and sustainable process for application, especially for the conversion of biomass into useful chemicals. I mentioned about 5-HMF, conversion of oil into biodiesel, conversion of the byproduct glycerol into useful chemicals such as glycerol tert butyl ether, The glycerol tert-butyl ether can be added into biodiesel in order to obtain high quality biodiesel because GTBE can increase the certain number of BDF. Thank you very much for your kind attention. I am open to any questions that you may have.